Is it not getting recorded? I think so. Yeah. Okay. So let us record it. I have started recording it. But can you see my screen?
Yes, sir.
Okay. So in the last class, we are talking about that aspect of usefulness of a drive, and we saw how it is useful in the case of a pump application. The pump characteristics for a certain speed is something like this, and you can alter the characteristics. You can alter the characteristics at running at a different speed. This is head. This is the pressure head, pressure, and this is flow rate. This is the pressure and this is the flow rate, and this is the pump characteristics. This is pump running at a speed, let us say omega 1. Then you can create such kind of characteristics, as many characteristics as you need by running it at different speed when you have electric drives. Okay, so the advantage that we saw is this, that if this system characteristics, that means the pipeline, etc., is like this, then the intersection point is the point where they will be working. That means I have to start again, sorry. Okay, can you see my screen now? I have lost the previous screen, but is it okay? Hello, please say yes.
Yes, sir.
Yes, sir.
Okay. So what I was doing is that we have this thing. This is the pressure, and this is the flow rate. In fact, GPM, volume, that is the gallon per minute. That is the normal unit used, and pressure is water head. It measures in terms of water head. And this is the characteristics of the pump. It is normally more or less flat, a little droop, but more or less flat. Okay, so we can create such kind of parallel characteristics depending upon at running at different speed. By running them at different speed, we can create more or less parallel characteristics. Then here, so on and so forth, we can create such kind of characteristics, and your system characteristics. By that we mean the pipeline characteristics. Not like that. Not like that. I should have some DC shift. I should have some DC shift. That is called static head. So let me start from here, and it has characteristics like this. So you can see that we are getting, for every flow rate, we are getting just the optimum value of we are running it at the optimum value of pressure. We are not wasting any pressure in the throttle. This is the characteristics, system characteristics. System characteristics without throttle. Right. So we are able to run at the desired point of the pressure flow rate plane. In the pressure flow rate plane, we are able to run at the optimum. This much is required. For this flow, this much. For this flow of F1, this much is required. This much speed is required. Omega 1, F2, omega 2, F3, omega 3. F3, omega 3 corresponds to this head character, corresponds to the head that you are developing. Omega 1 is corresponding to the machine, corresponding to the induction machine. By running the induction machine at such and such speeds, we are able to create this kind of pump characteristics. This is the pump character. Blue one is the pump characteristics. Pump character, ISDS. So we have changed it from the things from the mechanical to the electrical. Mechanical way of handling this would have been to change the flow rate, would have been to use a throttle, right? Whereas in electrical way of doing it is we are changing the pump characteristic. There the pump characteristics would have been unchanged, and the and what would have changed is what would have changed is the system characteristics. By introducing the throttle, by using that valve, they would have changed that, and then by that means they would have adjusted the flow rate. But in this case, we are adjusting the electrical way. Electrical way means by running the motor, induction motor that is attached to the pump or coupled to the pump, mechanically coupled to the pump. By running it at different speeds, we are changing the pump characteristics as shown by some parallel lines in blue, right? And therefore the operating points are now here and here, right? And these are the heads. These are the y-axis is corresponding to the head. Y-axis is the head. So let me call it H1 omega 1, H2 omega 2, and H3 omega 3. Now, how much is the power saved? If somebody asks me how much is the power saved, so you know the power is actually in the mechanical terms, it will be a multiplication product of pressure and flow rate. That will be the in the mechanical way. So it is proportional to power saving. Power is proportional to, I am not bringing in the issues of some coefficient from this system, from British system to the MKS system. All those things I am not bringing in. That will do when we do some numerical problems. So they are just some constants. So for understanding of it is not required. We just need to know the relationship. So pressure into flow rate. In electrical term, that is equal to power is equal to torque into speed, mechanical speed. Mechanical speed. That is mechanical speed. That is the definition of this in this. So from these characteristics, we can see that how much is the saving. How much is the saving in this case, because we are able to move it. So if the pump characteristics original were like that, pump characteristics original means no speed variation of pump, or in other words of induction machine, then we would have operated at this point. Then we had to operate at this point. This would have been the point. In this case, this would have been the point. In this other case, this would have been the point, and the rest of the thing would have, and finally this would have matched. The red one I take, suppose red one is taking and it is matching here. So finally it would have been this point. This point. So with blue, These are the points that would have been its operating point. So you can see the difference in head, which is being wasted, which would have been wasted if it were running at constant speed. So how much is the power? Power is this into that, right? So power wise, this is the product of this head difference, power saving. I'm just talking about power saving. So power saving is therefore taking a pattern which is product of this into this, right? So you know there is no power saving corresponding to this point, because this is anyway intersecting the pump characteristics original. So there is no pump saving here. So we can qualitatively say this is, let me draw it another color. This is the thing where both the power of the blue curve, power indicated by the blue curve, and the power indicated by the red curve match, but otherwise it is taking something like this pattern. So the top one is just product of this. So top one is taking a shape almost like green one. So it will take a shape like let me draw with another color, maybe this color. So this is the power profile, right? And this is the other thing, right? So this, it is nothing but product. So this would be the saving of power in the if you operate with variable speed application, VFD application, with variable speed drive. If you operate the pump, then this would be the saving in power. The hatched portion is the saving. Hatched portion is the saving, because you are able to move from blue characteristic points to red characteristics points. So this will be the power saved. Power saved, right? Power saved. You may note a small thing that the difference in pressure is maximum here, but power saving is not maximum here. The difference in pressure is maximum at omega 1, but the power saving is not maximum. Why? Because the power is a product of not only pressure, but pressure into flow rate. So flow rate is also a factor. So it's a product. So product wise, maximum power saving is happening at this point, at somewhere here, not at this point. It is maybe happening somewhere later, maybe here. So this when you have to have a flow rate of this, that time maybe the power saving is here. But in general, you can see that as the speed is increasing, as the flow rate would increase, there will be less power saving. The power saving is essentially having more prominence in the low speed zone. That is a common sense, because low speed zone, the most of the pressure you are dropping in the throttle. So since the throttle is taking most of the thing, it is likely to happen in the low speed zone. But you cannot immediately conclude the lowest speed corresponds to the maximum power saved, because the power is a product of pressure and flow. So flow is increasing, and the correspondingly difference in the difference between the pump characteristics and the system characteristics as far as the pressure is concerned is reducing, but the flow increases. So therefore the power might be more power might be saved at some intermediate point, not at the lowest flow point, not at the highest flow point. It is sure that the highest flow point will be 0 power saved, because that time the system characteristics intersects the original pump characteristics. So you have to understand this aspect in this while you are calculating it. While you are calculating it, you should know that it's a product, that is what it corresponds to. Then I said that it essentially means from the electrical characteristics. This is what is the mechanical way of looking at it. From the electrical point of view, I said that you can think it this way. Think it this way because that is, from our perspective, it is more important. What is more important? that we know the torque speed. We love our things in, they love in their things or pressure flow in this plane, flow rate plane characteristics to look at that plane. But we want to look at it from the torque developed by the machine, by the running speed of the machine in this plane. So this is the torque developed, and the induction machine speed, that is omega, I will call it rotor. This is the mechanical speed of the thing. And you may remember that our characteristics is just this, right, this. So this is when this is called something called synchronous speed, WSI1. So synchronous speed is defined as omega s is the supply frequency into 2 by P. So where omega sin is defined as synchronous speed, P is the number of poles, and omega s is correspond to supply frequency. Supply frequency I'm using, I am meaning in radian per second. So it is not in hertz. It is 2 pi f. Where f is the this thing. Synchronous speed. Everything is, when I am writing omega, you have to think that it is in radian per second. The unit is in radian per second. So don't be confused by that. I mean omega s is equal to 2 pi f. F is the supply frequency with which the induction machine is driven. The supply frequency with which the induction machine voltage appears across the terminals. Okay, so so this is the torque speed characteristic. Probably you have remember it, and I will also come to a little bit refreshing those things and bringing out some of the interesting aspects of it. While for teaching the drives, we have to understand why we are doing such kind of controls, why we are trying to operate the machine with such kind of controls. So this is the characteristics when your supply frequency, your supply to the machine is at the same frequency as the supply frequency. But with electronic means, you have seen that we can shift the characteristics. We can run it at a different speed. We can use a different synchronous speed. We are basically changing the synchronous speed without changing the pole. Because we are changing what? We are changing the supply frequency. If I change supply frequency, correspondingly omega s changes, and the omega s changes, correspondingly omega sin changes. We are not changing the number of poles. Number of poles is a mechanical construction. We cannot change the number of poles. So what we can change is this frequency. So electronically we will have the ability to change this frequency. So I will show you how, but for the time being, let us say what we are intending to do. We are intending to do is that we wanted to shift these characteristics like this. Right? We wanted to shift the characteristic like this and change our operating point. Change our operating point, implying that suppose the operating point now would be looking like the characteristics of the overall mechanical system. From our perspective, we now be looking like torque speed plane. It will be looking like this. So originally, if it were working at this kind of speed, it is the actual rotor speed at which it will operate. Given that the supply frequency is omega sin, or the synchronous speed is omega sin, this will be the this would have been the original operating point. But by shifting it, we are able to operate at this operating point, which means that the actual rotor speed has reduced. So actual rotor speed being reduced, the flow rate has reduced, and the characteristics of the pump that we desired in the previous figure we have obtained. So you see that the power has reduced. Power required by the system. What is the power at this point? At this point the power is, let me call it TD1 into omega rotor 1, that is the power, that is motor is this thing. And what is the power at this point? That is TD2 into omega rotor 2. So we have been able to reduce the power as we want. We don't want to waste it into the throttle. So we are reducing the power given to the motor to develop that flow rate. So this way you can calculate the energy saving from this perspective also. So what is TD1 into omega rotor 1 into TD2 into omega? Given the characteristics of the machine, you can understand that that you are operating the machine at a different speed, and you are able to save the what is that? Save the energy or power. Energy is just power into time. So now by looking at these characteristics, just let us take the original characteristics. We understand a few things. Let me remind you what are the things. So this zone is normally called our steady state operating zone. We don't never operate in this zone. We never operate in this zone. This zone is not to be operated because it is kind of unstable. Why do we say it is unstable? We say it is unstable because for some reason, you can check it yourself, I won't do it, you can check it yourself. For some reason, give a perturbation in the speed. So if you give a perturbation in the speed, you can see that here, if for some reason, if the speed increases, then the torque increases because it is in this slope. Speed increases, torque increases. So torque increases means it will further increase the speed, because our basic governing equation of torque and speed is J d omega dt is equal to torque developed minus load torque. This is supposed to be kind of, we call it load torque. This is the load torque of the pump, of the system, load torque of the system, load torque of the system that we referred there. Okay, so so this is the way the speed will continue to increase, and continue to increase means eventually it will come down to this part of the slope. And here you see that when the slope is negative, torque versus speed slope is negative, then you see that if you give a perturbation in the speed, this is the speed, this is the rotor speed, this direction is rotor speed. If you give suppose it is supposed to be operating here, suppose you give a perturbation and think that for some reason it has come to this point, then what is the tendency? Tendency is that the torque would be reducing. The developed torque would be reducing, and the developed torque it will be reducing means the speed has to now J d omega by dt has now become negative, right? The torque has reduced and therefore it is negative. So therefore load torque is now more than the developed torque. And the steady state TD is equal to TL. So then there it stays there. Then d omega by dt, and that is the steady state point. This is what is the equilibrium point, right? Now, but whenever you are going to a little bit position apart from that equilibrium point, you see either the developed torque is more or the developed torque is less. You see that the direction of this is nice, because if the speed is somehow increased, then the developed torque reduces as per the characteristics, as per the motor torque speed characteristics. So therefore, it has a tendency of again reducing the speed, because developed torque is reduced. So therefore, d omega by dt is negative. So it will try to bring it back to towards this direction. So for some reason, if it increases the speed has to reduce and come back to this operating point. For some reason, if the speed reduces, that means it shifts to this point, then the torque developed is more. Therefore, it would come back again to this operating point. So this is a stable operating machine, operates in this portion. Only thing is that we normally don't like to go into such high zone. There is a reason for that. We don't like to operate, though this torque is available as per machine characteristics. This torque is available too. So not naturally we'll say that why don't we operate at that point? So why we don't operate at that point? Because that this corresponding to this is what is the power that is given to the shaft. But actual power input, this is power, let us say call it, let me look little bit do it, you won't understand of it. Actually TD1 into omega rotor 1 is equal to P output of the machine. Output, that means it is giving the power to the shaft. Machine's job is to provide power to the mechanical system, electrical machine's job. So that is the power it is giving to the shaft. Whereas power input is TD1 into omega sin, that is the power P input from the electrical system, from the electrical supply source, the power is this. So what is the difference? This difference is TD1 into omega sin minus omega rotor 1. So that power is dissipated in the machine. In the machine means basically in the rotor copper loss. It is basically dissipated in the rotor copper loss. So I can qualitatively say that this area represents the rotor copper loss because it is TD1 into omega sin minus omega rotor 1. So this area correspondingly tends to increase. It starts increasing. It starts increasing if you shift your operating point to there. And overall, this increase doesn't increase the power that much. So overall, the efficiency decreases. Efficiency is output by input. So efficiency of a machine is output by input, right? If this ratio remains same, then the efficiency is same. But what we are seeing is that output doesn't increase in the same proportion as the input. Output power divided by the input power at when it is shifting its operating point to this place, because you can see that the loss is proportional to SPAS. Okay, the loss, machine loss is equal to S into P, right? S into P. So therefore this as we operate with higher slip, there will be more loss in the machine. Okay, so this loss in the machine will be will not be good for us. Therefore efficiency will be reducing, and therefore we will be operating. Normally we try to operate at low slip, not too low, but as such low. We don't really go beyond 3 to 4% to 5% slip. We don't really go beyond that slip. Slip is omega s minus omega sin minus omega rotor divided by omega sin. That is the definition of slip. That is the omega sin minus omega rotor divided by omega sin. So we don't intend to go beyond that. So that is what decides our operating thing, our operating point, that it is near to 4 to 5% at the most. We don't go, even though torque would be available, but we will not operate steady state, under steady state at that point, because it will increase the rotor loss, and that increase in rotor loss is not commensurate with the increase in the output power. Output power doesn't increase that much, right? So therefore overall the efficiency is reducing, would be reducing, and it will not be good for us to, my machine will become too hot and etc. The design will be extremely difficult, right? However, what we can do is we can change these characteristics, shift the characteristics by developing this electronic method, and we can operate at different this thing. Again, when we are operating at this point, you see that I have taken care that my slip is less. Again, the slip is not so much, okay, because slip is now with respect to this synchronous speed. We have changed the synchronous speed. We have changed the synchronous speed by not changing the pole, but by changing the frequency of supply. So you see that we have changed the synchronous speed again, and again we are getting good efficiency because this slip is again low. Okay, so this is what you would look for when you are using an electric drives for pump application. So with this, let me come to the machine and remind you how the torque and expression is, what the torque expression is, and how do we use it in our drives, that expression, how do we use it in our drives application. So let me start that a little bit, maybe refreshing your memory, and I will be talking only, I will not go into the derivation of basic electromagnetic field and then machine, etc., etc. I will be using some equivalent circuit to make my point. So the equivalent circuit, induction machine equivalent circuit, this is the equivalent circuit of induction machine, that you know, this is the stator resistance, this is the stator leakage, this is a per phase circuit, induction machine per phase. We have 3 phase, but each phase is considered to be identical, and this is the per phase equivalent circuit. This is the magnetizing reactance. Okay, we don't put iron loss here in the induction machine, we take it at the end. So iron loss is less compared to transformer, so that impact is not shown here. So this is the R1, this is JX1, this is the supply voltage. I am drawing this V1 implies the voltage in phasor form. This is implying current in the phasor form. This is corresponding to stator. This side is stator. This is stator resistance, stator. This is stator leakage. This is JXM, magnetizing reactance. Then we have rotor side leakage, JX2. It is not the total inductance of the rotor coil, it is the leakage inductance of the rotor coil. And by leakage inductance we mean the flux that is linking only the rotor but not linking the stator coil. The magnetizing current means, magnetizing flux means the flux that links both the stator and the rotor coil, right? So that part of this thing is here, and that part of current is magnetizing current, okay, which is responsible for creation of the effective flux, the net current. Actually current, both I1 and I2 creates flux in the machine. It has to, because there are 2 coils, and the stator current being I1, it is passing through stator coil creating flux, and then there is a rotor current that is passing through rotor coil and it would be creating flux. There is no doubt about it. The fundamentals don't go haywire. But the net flux, most of the fluxes created by the stator current and rotor current cancel each other. And what remains is one effective flux called magnetizing flux that decides the flux level of the machine. When we talk about saturation, we talk about that, the effective flux that is linking the coil, because most of the fluxes created by the stator current and rotor current are cancelling each other. They are related to the load currents, so they cancel each other. But what remains is the flux that originally remained without any load also, right? So that is the flux level of the machine, and we always, in previous class also we talked about that we must maintain it constant in order to maintain the machine at the maximum possible flux level without saturation. So our intention is not to saturate the machine, but to get extract maximum torque out of the machine at the minimum current. We must also try to place the flux at the maximum possible level. Okay, so so that's why a new conceptual current has come. That current is responsible for the effective creation of the flux in the machine. So it is somewhat like I1 minus I2. You can common sense wise you can see that I1 minus I2 will cancel, because I2 corresponds to the load part of the current. So this is leakage. So this is I may put it dash just to imply that there is a number of turns involved in this equivalent circuit. But sometimes if I forget to write that, you imply that you understand that I mean it. Okay, so this current is I2 dash, just to imply that there is a number of turns into this expression, and then this is R2 dash. This is physically rotor resistance seen from the stator. Okay, this equivalent circuit is with respect to the stator, so that's why the dashed secondary side quantities or the rotor side quantities all are written with the with one dash, right? But R2 is the physical resistance, R2 dash is the resistance seen by the from the stator side, right? So this is R2 dash, this is the physical thing. Then comes, you know, the machine is actually shorted. So the shorting, due to the shorting, the mechanical power is converted, the electrical power is getting converted to the mechanical power, right? So therefore that thing in the model, the amount of mechanical power that is going out can be represented by a resistance, that is R2 dash into 1 minus S by S, so that overall the resistance appearing from to the machine is R2 dash by S. That is the equivalent circuit resistance, out of which this part is responsible for mechanical power. It's responsible, this part is getting converted, and this part R2 dash is responsible for indicating copper loss in the rotor. Copper loss in the rotor. Okay, so this is what the physical thing is. This power is entering, electrical power, and this represents, it is not here, I mean the mechanical power's electrical representation is given by this resistance. Whenever there is a loss in electrical system, we have to put a resistance as in the model. We cannot put inductor, we cannot put capacitor. We therefore have to model the loss in terms of one resistance, and that is what we have done. And the resistance is that the amount of mechanical power that would be available from the machine is given by the as if a loss has happened in an equivalent resistance whose value is R2 dash into 1 minus S by S. That is what it means, right? So total resistance seen by the machine in the secondary side is R2 dash plus R2 dash into 1 minus S by S, which is equal to R2 dash, right? So here R2 dash represents copper loss. That is the true resistance of the coil. This resistance, the R2 dash into 1 minus S by S, is not a physical resistance. It's not at all physical. But due to electromagnetic torque development, the torque will develop because interaction of the flux, magnetizing flux, and the current, rotor current, that will develop the torque, and torque will development, and then it will go into the speed more. It will develop the speed and run at a stable speed, or the equilibrium speed dictated by the balance equation of J d omega by dt is equal to Td minus TL. It will run at that point when J d omega by dt is equal to 0, that is Td is equal to TL, that is the equilibrium point. It will run at that point, okay? And at that point, this is the steady state equivalent circuit. This is the steady state. At that point, there is a conversion. Conversion has happened, right? And that conversion is essentially a mechanical, it represents a mechanical power. So that thing, when I put into the circuit, I have to put into the circuit. Otherwise, if I don't put into the circuit, it means that there is no power conversion. So that model, the mechanical power that has gone to the mechanical side, is being now represented by a fictitious resistance, and it is derived as, it can be derived as R2 dash into 1 minus S by S. It can be derived as that mechanical power. If we equate, I get that value in the electrical representation. So you must understand that it is not a physical thing. It is just representing the physics of power conversion. Physics of power conversion from electrical to mechanical. It may also represent a physics of power conversion from mechanical to electrical, where the S term becomes negative, because the machine then runs at a higher speed than the synchronous speed. That omega sin becomes less than omega rotor. Omega rotor, then it becomes a negative thing. So that negative thing would be meaning that power is reversed. That means the power will be going from the mechanical side to the electrical side. Okay, so this concept should be clear in our mind, that what is physical resistance and what is non-physical resistance, but a model which represents the power flow. Ultimately, looking at this, you cannot see how mechanical power is going. Can you see? It's an electrical circuit. Where is mechanical thing here? But the mechanical thing has been brought into the thing in terms of a resistance, and fictitious resistance, and that fictitious resistance value happens to be R2 dash into 1 minus, that is why it is such a funny value. It is such a funny thing, 1 minus S by S, right? So and sleep is sleep. This is the sleep of the machine, that is omega synchronous minus omega rotor divided by omega synchronous. This is the synchronous speed of the machine. This is supply system is just V1, maybe a little bit more clarification we give. We give that supply voltage, supply is this thing is omega S, that is omega supply from the supply frequency of the stator voltage, that is omega S, and omega S is equal to omega sin into P by 2. P is the number of poles. So looking at this, if I want to one more time quickly tell you how we approximate this equivalent circuit and how we use it in our meaningful application. In the meaningful application, you must understand that we are operating. You must not forget that this part of the characteristics as if is meaningless to us. We are only operating at this part of the characteristic. That too at very low slip. Our operating zone is very low. This zone. Any torque variation is happening here. So that's why sometimes we see they say that the induction machine is a constant speed machine, because you see that the speed is hardly varying. In this small zone, the torque will be varying, but hardly the speed will be varying. Induction machine is sometimes, because you must understand that this zone is much extended. This zone is much more extended than this straight line zone. This straight line zone also has a meaning. Why this straight line? Why the characteristic torque speed characteristics is almost linear here? Here you can see that characteristics is almost a straight line. Okay, why it is so? That also we'll try to explain, because this understanding is important from the perspective of electric drives, right? Right. So let me do this. Start this derivation a little bit quickly. I will do it quickly. So right. So what is the output, mechanical power output from this expression? So mechanical power output, if I look at it, power output from this thing, I can say that it is nothing but I2 dash square per phase. I am writing 3 phase will be just multiplied by 3. I2 dash square into what? R2 dash into 1 minus S by S, right? R2 dash into 1 minus S by S. So torque output, that is torque developed, TD, would be what? I2 dash square into R2 dash 1 minus S by S divided by the mechanical speed. Mechanical speed means omega rotor. So omega rotor, what is omega rotor? Omega rotor, we can see that is equal to 1 minus S omega S, omega sin. So this is I2 dash square R2 dash 1 minus S by S. From this expression, you can see that this is nothing but 1 minus S omega sin. So this 1 minus S cancels. So this is equal to I2 dash square R2 dash by omega sin. This simple torque expression we should remember. Because it helps us in understanding many things very clearly. You should you don't have to take lot of complicated.
Sir, you have forgot S.
Oh yeah, thank you. Yes, I have forgotten this. R2 dash by S. Yes, S is very important. So R2 dash by S divided by omega c. So this simple expression you should keep in you because it's not difficult to remember. You don't have to think too much. It is somewhat like common sense. Common sense is that you look at the power level here. What is to be observed is common sense is saying the power is this. Power is this. In fact, power is this. Power is based on this current. That power is going. But torque is not based on this current. Torque is based on this summation resistance. That is what you are little bit learning, right? Because of what? Because the rotor speed is not equal to synchronous speed. So there is 1 minus s and 1 minus s in the numerator as well as in the denominator. So they are cancelling each other. Save, otherwise sometimes it goes out. Okay. So so you must see that I2 dash square into R2 dash by S is not really the power that is output to the mechanical system. It is the power, total power consumed in the, or total power coming out to the rotor from the stator, because that includes the rotor copper loss. It is not only the power that is outputted to the mechanical system, but it is also its own consumption due to rotor copper loss, which we cannot avoid. So that divided by synchronous speed is not the rotor speed, not the rotor speed. We have changed. That divided by the synchronous speed is the torque that is developed. So now comes the issue, if I want to further develop, what is I2 dash S square? So I2 dash S square, if you look at it very correctly, if you want to do, then you have to do a Thevenin equivalent, because you see, you are seeing from the rotor side, you are seeing from the rotor side, you have to take the Thevenin equivalent of this part of the circuit. You have to take Thevenin equivalent of this part of the circuit. So qualitatively, the Thevenin equivalent, I write it by one suffix T. So then this is R1E, Thevenin equivalent I have doing. Then JX1E, the voltage supply is now V1E. Let us say E means equivalent, Thevenin equivalent. That is the voltage supply, slightly changed. And then it has become a series circuit. Series circuit is what? Series circuit is X2J, X2 dash, and then overall this is R2 dash by S, and the current is I2 dash, because I have done a Thevenin equivalent. And Thevenin equivalent, this you know, it is nothing but this one is nothing but R1 plus JX1 parallel with JXM. This is nothing but R1 plus JX1 in parallel with JXM would mean R1E plus JX1E. That is how we have to find out. And similarly, you know how to find out also the you know how to find out the supply voltage, which is also slightly open circuit voltage. You understand that this open circuit voltage means you cut the load part. Load part is here. Load part of this thing is there. This part is the load part. You cut it and see the open circuit voltage. That means JXM by R1 plus JX1 into V1. That will be V1E, right? We are not too much bothered about this type of minor. Concept is more important. We are trying to develop that concept, right? So this is what is the expression. So looking at it very accurately, if I want to write, I will write TD is equal to I1 square. I am writing it as now. What do I write? This is V1E. I square is V1E magnitude square divided by square root of this. It was there, so it will be R1E plus R2 dash by S square plus X1E plus X2 dash square. This is I square into R2 dash by S and omega sin remains, right? So this is the actual expression of the torque if I want to do it very accurately, right? Right. So from here we also know that by this time that by applying maximum power transfer theorem, but very cleverly, because maximum power transfer theorem we are applying in order to mean that maximum torque is generated, right? Why I am saying so? Because look at the expression of torque. The maximum power will be maximum torque will be developed if maximum power transfer happens with respect to the resistance R2 dash by S. Look at the R2 dash by S, because if this power is maximum, I square R2 dash by S, if this power is maximum, then there is a maximum power, maximum torque development. Maximum torque development is not happening when maximum power is transferred to I2 dash square into R2 dash into 1 minus S by S, not to the resistance representing the mechanical load, but the resistance representing the total rotor load, rotor resistance, total load, rotor equivalent resistance. Rotor resistance is R2 dash. R2 dash by S is the equivalent resistance. So when the maximum the maximum torque is developed, when maximum power transfer happens into the equivalent resistance R2 dash by S. By looking at the expression, we can conclude that. So when it will be happening? It will be happening when this impedance is equal to that impedance, right? So what we say that then for maximum torque development, we can say that it happens when R2 dash by S is equal to square root of R1E impedance, that impedance, square root of R1 square by x1e plus x2 dash square. So this is what the what would be the actual expression of maximum torque happening in the machine, right? So so this is for, and that particular this thing we call it S max. S max is not the maximum slip. S max is the slip corresponding to the maximum torque, right? So S max is therefore if I and the corresponding S max is we sometimes write it in terms of S max, just nothing but this one, that is equal to R2 dash by square root of R1e square plus x1e plus x2 dash. It's a ratio. You must understand that it's a ratio. You must feel you must be interpreting it in that term. It's a ratio. It's not any physical thing. It's a ratio, right? So if it is a ratio, we'll come to that, how it makes more sense to us and how we utilize it. Then let us take for the completion, I write T max is equal to, so T max, if we put S max there, we can find out T max, and that is equal to V1 what we say equivalent, V1 is square into divided by R1e plus square root of R1e square plus x1e plus x2 dash square, right? And obviously we have half 1 by omega sin, that is there, into 0.5. This you must not forget. I am not right. This is per phase. So whenever you take 3 phase, you have to multiply it by 3. So this is what is the exact equivalent exact maximum torque, that exact value of the maximum torque considering all the stator components, stator resistances, and this would give you this kind of curve. So ultimately the point is that it will give you this kind of curve. It will give this, if I plot now, I will get this kind of curve. I will get this kind of curve, where this would indicate T max, this would indicate S max, this indicates S is equal to 0, this indicates S is equal to 1, that is the starting point, this is the developed torque, TD max, let me suffix it TD because it is developed torque, TD. So this is TD max, and what else? This is slip is equal to 0, and this is the expression. Anything will work steady state, under steady state, when there is an intersection of this with the load curve. Okay, but let us now try to see. We have seen that, we have argued that this portion is not useful to us. So our portion, only useful portion is coming here, and now we'll argue that in the next class we'll argue that where to operate and why it were not operating at this time. I have argued that qualitatively, but I will find an expression of that saying that how this would be more meaningful to us. I don't have much time to start it, but you can see that it will be done by one approximation. That approximation is that the stator resistance part will be ignoring, and then we'll see that this equivalent circuit, if you look at, I will give you a hint what I am trying to say, that first look at the equivalent circuit, think about it, look at the equivalent circuit, think about it. First of all, this equivalent portion, this R1, JX1 and in parallel with JXM is hardly changed the values of R1, X1. It has hardly changed because JXM is much more, XM is much more than the numerically much more than R1 and X1 in ohmic values. They are much more. So it is equivalent to R1 and JX1 in a series form. The series circuit, these values are there, right? Now you understand that when you are coming closer to the right hand side, S is increasing. What is that? Sorry, S is reducing. As you are coming to this stable portion of the curve, as you are coming to this portion of the curve, what is essentially happening? S is reducing. So what is happening? That R2 dash by S is continuously increasing. So if the R2 dash by S continuously increases, this becomes more dominant over the other circuit parameters like R1, R1E, X1E, and even X2. As we move closer and closer to the sleep is equal to 0, now you think that you have operating at a sleep of about 4%, 5%. So at that point, what happens? This R2 dash by S dominates. This value dominates over the thing. So the current is essentially decided by V1E divided by R2 dash by S. So we will be making this approximation because we are operating in that zone, in that specific zone. We don't operate in the long zone of positive torque speed zone. We are operating only in this zone, and we'll also operate in this zone because we'll see that the loss in the machine is proportional. Since the loss in the machine is proportional, the copper loss in the machine is proportional to the slip. So therefore, it is beneficial to operate in this low slip zone. But we cannot afford to operate in zero slip zone. Zero slip zone is implying that it will be zero torque. So we will operate at low slip in this zone, but not at zero, because zero slip is suggesting that the as per these characteristics, it is suggesting that the torque is equal to 0. So our intention will be to operate in the low slip zone, and in the low slip zone, the parameters of R1E, X1E, and even X2 do not matter. But because the equivalent circuit turns out to be R2 dash by S, right? Where slip is very approaching low. So our expression of the current, our expression of the torque becomes quite simple. So that part I will highlight in the next class. Thank you for listening.
Hello, sir.
Yeah.
Sir, I have a doubt in the like just above R2 dash by S equation.
Mm-hmm.
Sir, just go a little above in this page.
Where to? Can we?
No, no, sir. Like just below, like for max torque development part.
Oh, okay.
So, sir, there it is R1 E square here. So R2 dash by S vanishes. How? Like I don't know.
Up to that. Oh, it is application of maximum power transfer theorem. Maximum power transfer happens. You don't remember that source resistance, load resistance equation? That when there is a source resistance and there is a load resistance. Suppose DC, I take a DC. V. When is the maximum power transferred to this?
When RS equals to RL.
So that's what that's what I
Yeah.
did.
Sir, there is like one more part now, like R1E plus R2 dash by S part. This one is also will be there.
No. This is the load. This part is the load. I want to know how maximum power is coming to this load. It will come when this impedance is equal to the impedance of this part. This impedance is R2 dash by S is equal to the remaining. Then R2 dash by S again doesn't come.
Okay, got it, sir.
Source resistance is equal to load resistance, right? This is equivalent to the load. This is equivalent to the source. So condition is load resistance is equal to source resistance, right? So that's why I wrote R2 dash by S is equal to this. This is the source part of the resistance. Exactly the way we do it for DC in case of DC. Is it okay? Is it?
Yeah.
Is it?
Yes, sir. Yes, sir. Got it.
Thank you. Thank you. So